Hello and welcome back to Calculus 1 for the very last time. There we go. Now it's the last. It's the final exam review. Next time we meet, it's the final exam, and Calc 1 is over.
You could actually stream again. Just stream us struggling. Just point the webcam at us on the final exam.
Here is the misery, right? You'll do fine. So, we talked about the final exam review, limits, derivatives, integrals, most important sections, and all of those things. Make sure you're looking at the learning outcomes on your syllabus. Most of you should be concerned with word problems. We'll start with word problems because it's modeling and calculations, right? So the volume of the cube. This is one of the homework exercises from way back. So this is now 3.11 section, right? We are talking about related rates. And they say the volume of the cube. So I'm just going to draw the cube to have this image in my head. I know that the cube has side A, and side A. So three sides. Cube has all sides the same. And they said the volume of the cube. So immediate response in my head is to write the volume for the cube. Length times width times height. So the volume of the cube decreases at a rate of 0.6. Great. They said the word rate, right? So the volume will decrease at the rate. This is the way to write the rate of the cube, right? Of the volume. And they say decreases, so it's going to be negative 0.6. And they say feet cube per minute. Now, the fact that they gave me units, I can check if my name for this particular number is correct. We see the volume part and we see feet cube. Feet cube, that's a volume, so that's good. And then we see the time one on the bottom. Minutes is unit of time. So that's good. And the minus sign over here means decreases. You really don't have to put it there. But then, you know, the answer, you either have the minus in the answer or you have the minus verbally, again, stating the word decreases. What is the rate of change of the side? The rate of change of the side. So this is the rate of change of the side. When side is 12 feet. Well, the good news about this problem is at least the units are all across the board. You don't want to see, I mean, you can deal with it, but, you know, feet and inches, and then you have to convert stuff. Or one is per hour, the other one is per minute. Again, convert stuff with 60. And so on. So it is not just, you know, the concepts in terms of, do you know the volume formula, perimeter formula, surface area formula, but it's also, do these units match? And if you remember, I believe I did that evil thing on one of your problems on the exam where I combined millimeters and centimeters just to see who was paying attention. I didn't do it on all problems. I could have, right? I did it on one. Because you really don't want to design your space shuttle, right, in meters and programming in feet, and then, you know what I mean, right? Good. So we have a cube that is shrinking because the volume is decreasing, that negative 0.6. Now, it should be common sense that you would expect side to shrink as well, so we are hunting for the negative number. Now, all of these problems are the same. Once you are familiar with the concept, in this case, volume of a cube, you also see that the derivatives that you are requiring are all derivatives in respect to time. So, your volume formula is going to get differentiated in time. So now you get dv dt is equal to 3a squared. That's just a standard derivative, 3a squared. But it's an implicit differentiation because a is a variable and it's changing, And now we're changing that in time, so dA dt is necessary as a chain rule. So it was the implicit differentiation that dealt with this particular formula. And you actually see all of the numbers that need to be plugged in now. So dV dt, so that's negative 0.6, is equal to 3 times, and now you have over here 12 squared. And dA dt stays as the unknown, but that's what we actually want to compute, right? So that's good that we have it. And without actually me going and figuring out decimals and whatever, who cares, dA dt is going to be negative 0.6 divided by 3 times 12 squared. And whatever your calculation works out to be for this. And it's going to be feet per minute. It's going to be feet per minute because it's side. So this is the exact answer, and then you can go canceling and doing your decimals and stuff. So again, you should look into a sphere, a cube, right? Cylinder, right? The other things like cone, you know, end up being a little bit more, right? But definitely, I mean, if you are practicing these general problems, you must know sphere, must know cube, and must know cylinders. Now there's a cone, but cone has the product rule and all of these kind of things embedded, right? Because for the cone you change the radius and the height at the same time, and that's involving more complex calculations, which is less probable at that. But
I think what was confusing is that I put volume equals base time. No, I just wrote everything. So base times height. And
okay. Well, it is base times height. It's the area of the base times height, but the area of the base is again a times a because it's square, right? So all sides are, so you have a times a times a, which is a cube. But the overall formula, I mean, you were not wrong, it's just you didn't know what to do with. Yeah. Anything else? Yes?
There is a problem in the lab. This is a general question. So if there is a acceleration given with the formula for that, and we are given the velocity at time 0 and the position at time 0, then how can we find the position function from the acceleration height?
Well, you integrate. So the question is the relationship. So on your lab, the question is to find the position function from acceleration function. I wrote this diagram at, I believe, 2 different occasions in this class, where you start with the position function in terms of time, and then you differentiate that function in time to get the velocity function, and then you differentiate it one more time to get your acceleration, right? But then you can also, here in blue, you can also, from acceleration function, you can integrate acceleration function dt to get the velocity, and then you can integrate velocity function dt to get the position function. Now, remember that when you integrate this, you will get plus c every time. And those values, the extra values that you are getting, are the values that you will use to compute plus c. So that the initial condition. So I know that I derived in class, if you start with your acceleration of gravity, right? A equals gravity. Let's put negative g. And then I said, you write this a, you write a as a change in velocity over change in time, because that's what acceleration is. You are changing velocity, you're changing your speed. When you're driving, you have 2 pedals. You have acceleration pedal, gas, and you have deceleration pedal, which is brakes. Both of those change your speed. So you're technically, you know, stepping all of the second derivative, right, when you're in a car. So if I have this situation, now if I transport this dt to the other side and integrate both sides, right? Actually, I'm going to put the integral red. Integrate both sides. What I get is that the velocity is equal to negative gt plus some constant c. And this is where the velocity of, let's say, 0 equals 5 kicks in. Because you plug in 0 for t, and you plug in 5 for velocity, you see that you can calculate the number for c. So that's where it kicks in. So, I don't know, let acceleration function be a of t is equal to x squared minus 3. And let's say you have that the v of 0 is 9. So what you're going to do is you're going to integrate acceleration, which is the integral of x cubed minus 3. I was supposed to say t squared minus 3, not x. There we go, much better. T squared minus 3. So you integrate this, and you get t to the 4 over 4 minus 3t plus c. Right, this is what you get. And then, so now you actually got the function velocity of time, well, v of t is equal to 1/4 t4 minus 3t plus c. And now you have to use a v of 0 equals 9. So you see v is 9 is equal to 0 minus 0 plus c, from where you get that c is equal to 9.
Wait. How did we go from t squared minus 3 to t?
Oh, you're right. That was supposed to be a square. Cube. I could have fixed it up there instead of fixing everything here, but that's okay. Yeah, you're right. I copied the wrong, because I was already solving this. I solve it in a second and then I move on. All right, so we have t squared minus 3. And t squared minus 3, so it's 1/3 t cubed minus 2, but you have this plus c. And this initial condition allows you to compute that c as a value. Now, if this was a different number, right, number different than a 0, right? Other example, say velocity of 3 is equal to 7. I don't care, right? So then in that case you would have 7 is equal to 1/3 times 3 cubed minus 3 times 3 plus c, right? So you plug in whatever time is given to you. In this case, in blue case, now time is 3. You plug that for each t, and your v is equal to 7. Well, that goes on the left hand side. So now you have 7 is equal to 1/3 of 27. That's 9 minus. Oh, so I keep getting the same value back. It's not always the same value back. It's just two bad examples. Whatever. So your velocity function now of time is going to be 1/3 t cubed minus 3t plus 7, because we calculated 7. And then you can go on and compute the position function. You integrate each one of these, you'll get the plus c, use another initial condition to calculate, right? So you can have as many as you want. As many levels. You can start at the velocity and ask for position and acceleration. Well, if you're starting with velocity, you're going to differentiate for acceleration, integrate up. Right? You can start anywhere. That's why learn the string, right? Position differentiated is velocity differentiated. And actually that makes sense. Think of the units, right? If your position function is measured in meters, or let's say, well, miles, So if your position function is measured in miles, then your velocity is the derivative in respect to time, miles per hour, right? Units work. And then acceleration, miles per hour. You'll know it as meters per second squared, right? Because generally that's what you use. But you also have feet per second squared. You have, you know, miles per hour squared. All of that is acceleration. You can convert into anything. So applying the derivative is just going to be, this is in meters, and then here's your over second when you take derivative, meters per second. Now this is meters per second, and then you do another per second, and it becomes meters per second squared. So dimensional analysis makes a joke of certain classes that you take. If you know how to deal with units and you understand these basic concepts, there's very little that you need to do in physics and general chemistry. Just take show up. When they give you a question in general chemistry, they include the units. You can always back engineer the formula. You talk about densities and, you know, molarity and stuff like this. The only place where you have to put some effort is, you know, the reaction equations of what you're going to get. Not balancing. Balancing is just common denominator. So, you know, knowing a lot of mathematics, going into these courses like general physics 1 and 2 and general chemistry 1 and 2 is just a joke. Where analytic physics, calculus-based 1, and then organic chemistry, which I never dare take, those could be really, really interesting, and challenging.
Analytical physics is different from general physics a lot.
Analytical physics is calculus-based. So all
you don't take engineering students don't take general physics, I think.
No, because it's like an introductory physics. But there are a lot of majors that will need that physics. There's no reason for biology major to take calculus-based physics, because biology major also has only Calc 1 as a prereq, and then some schools would ask for Calc 2. So bio student cannot perform to the same, like there's no way that the bio student can in analytical physics deal with alternating currents and flux and all. It's the whole calculus 3 calculations with the double integrals and surface integrals and stuff like that. So, but then the tables turn later. You know, on a graduate level, if you're learning mathematical biology, that is the scariest field of mathematics in terms of applied math. Mathematical biology, and the hottest field too.
Professor, so for derivatives, just the basic ones for trig?
For derivative, yes. The basic derivatives involve all. When I say basic derivative, I mean you must know the derivative of e to the x is e to the x. Derivative of tangent is secant squared, right? So all of that falls in the basic derivatives. And then you go and you say, right, I understand that we had a separate section on trig derivatives, separate section on log stuff, but basic derivative is just to know that the derivative of ln x is 1 over x. That's basic, right? And then it might be scattered over 3 different sections, but the basic ideas are basic ideas. And then you have the chain rule, product rule, quotient rule, implicit differentiation to combine those basics. And then you use them for tangent lines. Then you use them for these kind of things. Yes?
Can you show us the antiderivatives that are related to inverse trig functions?
Are we doing inverse trig functions?
The only two that pop up is sine and tangent, inverse sine and inverse tangent.
MATLAB asks about them.
Yes. So the only two that pop up, but I already showed briefly where I reviewed in my calculus 2 class, where we found by hand the integral of inverse tangent. So this is one of those things where you memorize formula for a little while, and then you don't worry about it later because you know how to get the formula.
I know that for tangent, for example, you replace it with sine over cos, integrate it out. But I'm talking about things like 1 over 4 plus x power 2, and it's
Yeah, that's inverse tangent. Yes,
yeah,
yes.
yeah.
So well, here
I
is the,
think there are formulas for it.
yes, yes. But what I'm saying is that in Calculus 2, you learn in section Trigonometric Substitution, you learn the way to deal with it. So that's why. So your question was exactly this: 1 over 4 plus x squared dx. Right. So this is something that you have to memorize in Calc 1. And generally, the only two formulas that you will be memorizing are the ones that I indicated, which are the inverse sine and inverse tangent. And this is inverse tangent. So if you look at this thing, you will go with the formula which says that the integral of 1 over a squared plus x squared dx is equal to 1 over a inverse tangent of x over a. I can't fit the solution because I need to put plus c. So equals to 1 over a inverse tangent of x over a plus c. Now, when you carefully look into this problem, you see that your a is equal to 2 because you have 4, right? So this is a squared if you pay attention, right? So if a squared is equal to 4, then a is equal to 2. So maybe I should just do this. A is equal to 2. So now this immediately equals to 1/2 inverse tangent of x over 2 plus c. And that will be the end of the story. No calculations. You either know it or you don't know it. Now, moving to Calculus 2, you compute this problem from scratch. So you go into trig sub, right? And this problem is much harder, obviously, but you see the same structure of x squared plus a squared, right? So, and you see me working with a tangent, right, which has to pop up because that's the situation. So these are type of the things that will be addressed in detail. So again, it's one of those where you learn a formula for a little while and then you can let go of it when you learn more powerful techniques.
So do we have to learn the derivative, the inverse?
Yes, tangent and sine. Those two.
No, and not this one, the other one.
Well, when you know one, you know the other because you just read it backwards. The derivative of inverse tangent is this. So you immediately know both. So you have inverse sine and inverse tangent to worry about, whether you learn them as derivatives and then write them backwards as integrals, or you learn them as integrals and write them backwards as derivatives, whatever. They will be featured in differential equations, of course, and Calc 3. So strap on for that ride too. Anything else? Yes.
Yeah, so we haven't done chapter 5 for the guys, so I was just thinking, like, can we just go with the finding the net area and area of a simple function?
Well, the definite integral is the net area. So when I asked you to compute the integral of sine x from 0 to 2 pi, you got 0, right?
Okay.
Exactly, right? So that's a net area because you have the one bump above x-axis and the one bump below x-axis, and they're identical, right? So they subtract to 0. That's not always the case. You can come up with functions where they're not going to cancel. So if I take a perfect x cube like this, right? I didn't draw it nicely. Still. No. Yeah. All right. So again, plus and a minus and the area equals to 0. But then I can have a cubic function that does this. Whee! Right? Well, in this case, it's not equal to 0, right? But it's not the area that you shade, right? Because this minus part will take away this much, right? So you'll be for this much wrong. So you have to be careful what question asks. If they say area under the curve, well, then you have to play the game of what dips below where and then make the absolute values and all that kind of stuff. Right? So sine of x dx, right, between 0 and 2 pi is equal to 0. Now, you interpret this question in two different ways. You can say net area, or you can say value of the definite integral, right? So that's the way. But you also have this case, when equals to 4, we just say area. We just say area. So if I say find the area under the curve, then you are playing the game of absolute values and everything else, making sure that you have every piece that you can color accounted for. Below or above, x-axis, doesn't matter. If it says compute the definite integral, well, that's the net area, and we actually don't care about figuring out the area. We want to know the total, right? Because you have a positive energy, negative energy, right? And I just want to know the full, all of the energy, right? I'm not going to look into details, right? So the net energy in this case is 0, right? Because we took potential and kinetic energy, maximum potential energy, here's kinetic kicking in, and boom, back right where you was. Positive energy to put it up, negative energy to go down, altogether 0, right? So that is the concept of, right, so just be careful with the wording. If it says net area means just the basic definite integral, nothing special, just go up and down them, right?
Now, for 4, you can just do from 2 integrals, so it's going to be from 0 to pi, and pi to 2 pi, right?
Yes, and the pi to 2 pi would be under absolute values because that's the part that dips below.
Okay, so anything that's below the x-axis, we always put that in the...
That gets the absolute value because you need to add them all up.
Now, if you just say area, then we can indicate that there is a regular area, not the net area, right?
Exactly. Area and not area are not the same thing. That's why you have different things for the same, what would you perceive. So that, calculus is not just monkey sees, monkey do. You have to think about questions. You have to be, critical and observant. So if I'm asking for the value of the integral, you just do it. If I'm asking for the net area, again, just do it. But if I'm asking for the area, that means I want to color. I want to color every square inch of it, right? You have to account for every square inch. Anything else?
The last one. So from...
I'm here to service. I'm out.
Okay.
I'm out. Shower in 10 minutes. So. I'm not in a rush.
So from chapter 5, except along with U side and this area, what else should be accounted for the final test?
Well, first of all, you have definite integrals. Definite integrals are 5.3, and you, instead of putting plus c, you're computing, right? Now, at the same time, one of your learning outcomes says one of your learning outcomes says fundamental theorem of calculus. Fundamental theorem of calculus consists of 2 parts, one of which is definite integral. So computing a definite integral with computing the limits, you bet your life on it, right? That's right. Whether it's going to be the part 2 of the fundamental theorem of calculus where you have the derivative of the integral, it could be there, it might not be there, right? In which case, they would double up, right? Which is okay. I mean, it's fine to have both. So you are definitely banking in chapter 5, especially because you didn't have a test on it, right? you are definitely counting on having definite integral to compute, and then basic integrals with plus c, which are from 4.9, and then at least 2, I would say, right? At least 2, like part A, B, or something, on U sub, right? Maybe very basic, easy, something that you do in a minute, and then one a bit spicier that will take you a little bit longer. But you have to expect at least, 5 or 6 integral signs or concepts, right? Like the one with the velocity or something, right? Where you have to integrate. Little bit less probable would be the average formula for integrals, and then those special formulas we learned on a symmetric interval. That's pretty much, because you can do it. If I give you the integral from -2 to 2, you can just do it. You don't have to remember the formulas, even, odd, and do all of that stuff. Later in mathematics, that saves your life in terms of cutting out a page of calculations, but now, for 3 lines, ciao. So that's your chapter 5. No Riemann sums, and you do not have to memorize those formulas for sums. For sums of sums.
We have to show all our work.
Yes, because some of the points are allocated for the milestones, should I say, right? So, for instance, if you have related rates question, right? 1 or 2 points allocated towards your formulas, and then 2 or 3 points for calculations, and then 1 point for correct answer and 1 point for a sentence, let's say, in which you state dimensions are, and you just write out, right? So like a sentence answer for word problems. I'll make sure that that's also announced. Okay.
Okay, so my idea for the project.
Well, are we done with the review? Any other questions regarding any problems, any derivatives I need to take? Implicit or chain or product rule before we jump into project? Any integrals that I need to do? Any limits? For L'Hopital, 0 over 0, infinity over infinity, 0 times infinity. That should be, already infinity minus infinity takes forever and all of these, right? So you have to understand we have a bit shorter final, so probably those are very low probability that are there, but you have enough for limits anyway, so making sure that at least the basic L'Hopital rule is there. There will be enough time for you to cry and sob in Calc 2 if you don't know it. No, I'm serious. I teach that class for 8 years now, and I took it. So I know what that class is. Okay, let me see. What else? What else do I need? Again, bring some kind of sugar. Have it available so you can, in a liquid form or a solid form. Sleep. Man, people, sleep. So your brain's rested. Don't go studying 5 hours before the test and you come in brain dead because you used all of your mental faculties already before the exam, and then you say, oh, I confused everything. And you didn't confuse, you just brain dead because you were tired. That's actually what it is. the tangent line problem. So the tangent line problem, first of all, you will not be taking derivatives using limits. So the good old formula for the limit using the difference quotient of f of x plus h is not going to be there. It's there for honors. Yes?
Did they ask about any definition of derivative?
Unfortunately, no. Which means that you will not be getting any free points. I know. It's terrible. It's terrible. It would be much better if they did, because you score free points that way. I mean, there's no way that you can solve a product rule question if you don't know product rule formula. So if I'm asking product rule formula to be written on the exam, well, that's clearly free points. If you can't answer that question, you clearly can't answer the other one either, so no harm done, right? To those who didn't study, and definitely a benefit to those who did. So yeah. But anyway, so the first question was on the limits regarding the derivatives, and there will be no use of those to find the derivatives. All derivatives are either basic, product rule, chain rule, or something like that. And then the limits that you will be taking are the ones that are coming from these basic sections that we did. The second question was on tangent lines. One more time, when you get a function, let's say x squared plus 3, right? And you have the point at which you want to find the tangent line, let's say at 1, and you're looking for tangent line, you are figuring out the derivative first, which is 2x in this case, and then you will find the slope when you compute your derivative at the point that it's given to you, which is in this case 2 times 1, and we have 2, so slope is 2. Now you have x value, you have slope, you have a function, you can compute the y value, which is f of 1. In this case, 1 squared plus 3 is 4. And now when you look, you have m is equal to 2, and you have 1, 4 as the point. You can use y equal mx plus b, or you can use y minus y1 is equal to mx minus x1, whatever you like. If you're using mx plus b, so y is 4, m is 2, x is 1, plus b, from where b is clearly 2. Y equals 2x plus 2 as your as your tangent line. If you're using the other form, right, you will have y minus 4 is equal to 2x minus 2. Y equals 2x minus 4. No, this is a 1 over here. There we go. Plus 4, and there's your y equal 2x plus 2 again. Right, same. So whatever formula you like to use for tangent line, that's your algebra. I don't care what you use. Just get the tangent line straight, because it's a straight line. I know. Oh, you have no idea how many times I see. Way too many. Even if it's one student, it's way too many. Writing that the tangent line is equal to, 2 over x plus 7. The hell? 2 over x is not a straight line. Immediately you see immediately you see the failure all the way from algebra into calculus. You know what I mean? Your tangent line must be a linear line. No exponents on x, no exponents on y, no sines, cosines, tangents, e's, ln's, nothing. It is a linear line, y equal mx plus b, and you cannot put anything else. So it's not, let me take a guess and put the tangent line to be x squared minus 7. I mean, yeah.
How about oblique asymptote?
Which one?
You know, when it's not horizontal or slant, yes.
Slant asymptote?
Yeah.
Pre-calculus prerequisite. Yeah, it's all good. You just do law. Slant asymptotes occur only in rational functions where you have a polynomial divided by polynomial, where the exponent in the numerator is by 1 bigger than the right degree of the denominator. So when you do the long division, you end up with a linear line of the first degree. And that should make sense. So if you have x cubed over x squared, they cancel to a single x. There's your oblique line, right? If you have x to the 7th divided by x to the 6th, you still have it. If you have x to the 6th and x to the 4, well, your slant asymptote cannot be x squared because there is no asymptote that it's x squared. You know what I mean? So it only happens in those, and why not, right? So all of the stuff that we talked about in terms of functions, right? The graphing of the function, you know what it means when the function, well, the derivative, right, cuts through x-axis, it's a critical point. When the second derivative cuts through x-axis, it's an inflection point. Function above, increasing, decreasing, concave up, concave down, all of that good stuff, right? So that's all part of the learning outcome here.
So for the graphing, there is going to break the question as unit, right? You can have like one single question graph everything.
Well, no, breakdowns, yeah. Because you have it's two-sided, right? We had sections where we did analyze the graph, and there were sections where we did make the graph, right? So when you do first and second derivative test, you are analyzing the graph, right? Where is it increasing, where is it decreasing, and stuff like that. When we did working with the derivatives, if you remember, that was, I believe, 3.2, like 5 years ago we did it in this class. We talked about the functions, relationship between the function and the derivative, right? So I was able to sketch the derivative function looking at the basic without any calculations, right? We learned how to do that in detail in chapter 4, but we were able to sketch stuff in chapter 3. So all of those relationships, right, the horizontal tangency means the maximum, means the derivative is equal to 0, which is x-intercept, right, on the derivative. Like making those connections, that's good. But also graph ln x squared, that's good too, right? Because you can take some derivatives, first, second derivative test, right? Or give you what I give you, the chart of values with the vertical asymptote and so on, and you just do the asymptotes and points first and then connect the dots, right? That's the graphing part. Anything else? Because some people just want to go. Ten seconds. Come here, please. I'm not in a rush. It's just I don't want to drag it out if you know. But well, I guess I'll see you Thursday. If you are taking the final earlier because you must, good luck, and I'll see you around. I'm not teaching Calc 2 next semester, so you'll be probably taking it somewhere else. But then probably see you in the summer for Calc 3. Calc 3 is good for the summer. Calc 2, not so.
Professor, how long are the classes? The whole summer?
6 weeks. Yeah. All right, so let's say bye for the last
6
time.
weeks for each